Okay, so uh, today's lecture will focus on kind of just like practical aspects in terms of data preparation and feature engineering, things of that nature. Okay, so the idea in general is we have our training data. We want to make predictions on our test data. Okay, and um, actually, this will come later. But we want to, today we'll cover kind of like mostly creating recipes and pairing that with workflows. And we'll talk a lot about recipes, okay? This is reading from our textbook, Tidy Modeling with R, okay? Um, if, uh, if you're gonna do things in Python, these in scikit-learn, basically what Tidy Models calls recipes, scikit-learn calls pipelines. But again, it's the idea of you take raw data, you do some preparation steps, and then you fit your model. You don't just take your raw data and just fit the model directly, because a lot of times you have to do some pre-processing. Okay. All right. So anyway, we're going to load up our libraries, Tidyverse and Tidy Models. Okay, and then we've done the initial split of our data, and I guess I'll follow along in R as well. What's this? I accidentally clicked that. Let me clear everything out. So we're gonna load library Tidyverse and Tidy Models. I think they're already loaded. Okay, and then we're gonna take our AIMS data, and then I'm going to transform the sale price into log of sale price. Okay. And then we're going to split our data into a training set and a test set. Okay. And the train and the test, these are going to be subsets of our data, right? So we've got around 80% in our training and around 20% in our test data set. Okay, and here we can call glimpse on our data. So if I just do glimpse on AIMS train, we can see all of the different variables. And this is all kind of, but you see things like the subclass, which is going to be kind of, one story and newer, zoning, residential, low density, the lot frontage, the lot area, is the street paved or not, alley, lot shape, all kinds of stuff. All right, so these are just a bunch of the variables that appear. There's sale price, which we've taken the log of, okay, base 10 log, and then we have longitude and latitude. Okay, so, perhaps if you were brand new, then what you might attempt to do is you might just say, all right, like if I said, make a linear regression model, okay, one of the things you might do is you might just do something like LM, and then you'll do like AIMS $, sale price, and then you'll just do like tilde dot, right? Okay, and that's just like throw in all of the variables as predictors. Now, that LM function actually performs some pre-processing for you automatically. You don't even have to think about it, because it's going to automatically turn all of the factors into some kind of like a dummy variable where you're going to have zeros and ones, and that way you end up with other stuff. But normally, like if you had to fit a linear regression model and you're going to use like matrix operations and you're going to do something like X transpose X inverse, things like that, everything has to be numeric, right? And, obviously our values here are not numeric. And so pre-processing is the idea of like, okay, how do you take your variables here and do things so that they're in numeric form so we can kind of do mathematical operations, okay? And so one of those will be things like make dummy variables. Take any of our categorical variables and turn them into zeros and ones so we can do some operations. But other things will be things like, okay, we need to standardize them. We need to center and scale them, okay? And so that's where recipes come in, okay? So recipes is a package within Tidy Models, and it handles all of that kind of pre-processing. So we're not just taking the raw data and just trying to, multiply matrices on them, because a lot of times they're not in a suitable form. And so this handles all of those things. So things like transforming variables. So if you need to do any kind of like log transform or a polynomial transform, or even do spline operations, that works. Scaling variables is very important for certain models where it's sensitive to distances. Okay, converting categorical variables into numeric ones. This is, if you just use LM, this is handled automatically, but a lot of other models and a lot of other functions don't handle this step of making dummy variables automatically, okay? And then we may also want to impute missing values. So if you have missing values, a lot of times some approaches will just say, okay, we just have to ignore these observations. We just have to throw them out, okay? And then you have options for handling that. You can impute them, okay? Just fill in some values or things like that. And so there's a whole bunch of different things you can do as far as what we call a recipe, or basically pre-processing steps. So recipes is just the name that Tidy Models uses for these steps, okay? An important idea as far as why we need to use recipes is that we want to prevent data leakage during our pre-processing, okay? So data leakage is this idea that you are taking outside information, you're using outside information during the training process, okay? And if you do that, the model that you train will end up actually performing better than it really will in the test environment, okay? So like for an example, let's say you want to standardize or normalize one of your variables, okay? Common operation is to subtract off the mean and divide by the standard deviation, okay? The wrong approach would be to calculate the mean on the entire data set, and then you would calculate the mean and standard deviation using the entire data set, and then to use that during the training process, okay? And so now you have information about your test set or your validation set, okay? And this gets complicated. Well, does that kind of make sense? So let me, so if we think back to these concepts of like cross-validation, okay. So even during this during the training process, let's say we have done testing, okay? We have kind of split this off. And so we are still dealing only with the training part, but you still want to kind of perform cross-validation. And so within the training, we've done like this k-fold cross-validation, v-fold cross-validation. And as you're kind of evaluating your model performance, technically, you need to calculate, like when you do your normalizing operation where you're calculating the mean and the variance, mean and standard deviation, for the first fold, that mean and standard deviation should be calculated only on the analysis set. You don't want to calculate it on the entire training set, okay? Because then you have information about the assessment set that's going to kind of improve the performance of the model, okay? And so each fold requires calculation of the mean and standard deviation that then gets reused over here, okay? This fold calculates the mean and standard deviation on just this analysis set that then gets reused, gets applied when we do the assessment, okay? Does that process make sense? And so this can become cumbersome, and so recipes and pipelines and scikit-learn smooth out this process for us, okay? It eliminates a lot of kind of the headwork and the work, the legwork that needs to happen, okay? So the correct way, the right way to do this with a recipe or, a scikit-learn pipeline is that you, quote, learn the mean and standard deviation just from the training data, or in this case, the analysis set. When you prep your recipe, it saves those values, and then it's going to apply those exact same transformations to the new data set when you bake it, okay? So a common thing that happens is that, when you do this operation, you subtract off the mean and standard deviation, or divide by the standard deviation. On your training set, the resulting column will have a mean of 0 and a standard deviation of 1, okay? But then when you apply it to your test set, you're not necessarily going to have a mean of 0 and a standard deviation of 1, okay? And that's actually a good thing, because it means you didn't learn anything magically from the test data set without, and everything has learned only from the training set, okay? If your test data set has a mean of 0 and a standard deviation of 1, that is suspiciously, like, something feels a little bit off, okay? Because it just means, like, either your test set mirrors your training set exactly, or some information has leaked over from the test set during your training process, okay? And so, by preventing this data leakage, it says, it'll ensure that your model's performance on the test set is an honest and reliable estimate of how it will perform on new unseen data, okay? I guess, another way to kind of think of this is that as let's say you buy a, GRE prep book, right? And it comes with practice exams. And during kind of your process of, like, have I learned the material, you don't want to accidentally have, like, peeked at the questions and the answers for some of the other questions, right? You want to actually know, like, you've learned the material, okay? And so the way recipes works is we have these two functions, prep and bake, okay? So you write out your recipe as far as, like, what are all of the different pre-processing steps that we want to take, and then we use the prep function on the training data, and this is going to estimate all of the kind of necessary parameters for your pre-processing steps. It's going to estimate, like, again, during normalize, it's going to estimate things like the mean and the standard deviation of each column that you want to normalize, okay? As far as dummies, it's going to identify all of the factor levels and say, okay, we need a dummy variable for the color red, and we need a dummy variable for the color blue, and a dummy variable for the color green. It's going to figure out all of those things. And then when you bake it, you apply those kind of calculated transformations onto your data, okay? And so your process would look something like this. You have your recipe and you call prep on it, okay? So you have prep recipe training data, or you pipe recipe into the prep step, and then you store this as the prepped recipe, okay? So the recipe is just the steps. The prepped recipe has all of the parameter estimates that's going to get used. Okay, and then you bake it. Okay, and you take the prep recipe and you either apply it to your training data, and you call bake on this, and this is going to return your baked training data. So this will be your training data after you've applied all of your transformations, right? And so the result should be, a big data frame that's completely numeric that you can then process into, well, not necessarily completely numeric, but it's going to have all of these transformations applied that you can then throw into the model that you're going to use, okay? And then when it's time for the testing to run it on the test data, you do the same thing. You call bake with the prepped recipe, and you do it on your testing data, okay? And it's going to apply the same transformations that was applied to the training data to the testing data. So it's not going to relearn a mean and standard deviation from the test data. It's going to use the estimated mean and standard deviation from the training data, okay? And then now in practice, you don't actually have to call prep and bake, because generally we bundle these together in workflows. And so I had mentioned workflows like in our last lecture, where we talk about, the workflow does binds the pre-processing, the recipe, along with the model, okay? And that workflow will automatically understand how to prep and bake. Okay, so we are going to just start off with a very, very kind of basic recipe, okay? And so your initial recipe, there's a few ways you can start off with a recipe. And one is you can start with formula notation, okay? You can also specify, I want to select these predictor variables or things like that, but here we're going to do it in formula notation. And so this is going to just tell us in the recipe, what's the response variable, what's our predictor variables, all right? And so here we're going to say, I want to predict sale price. This has already been log transformed, okay? And we're going to try to predict sale price based on 3 variables, okay? Which is basically the size of the home, which is GR live area, gross living area. So basically, how many square feet is the home? The year it was built, and then the number of bedrooms, okay? So it's like, this house is 1,800 square feet with 4 bedrooms. This house is 1,500 square feet with 3 bedrooms, or 1,500 square feet with 4 bedrooms, things like that, built in this year. And so, so here you can do this, and you can just do recipe, sale price, gross living area, year built, bedrooms above ground, and the data is coming from the Ames training data, right? And at this point, it feels like, well, we don't need to use a recipe, all right? So this is very basic, okay? But the power of the recipes, again, really comes in when you do have these pre-processing steps, okay? And so if we ask, what does the recipe look like so far? So actually, let me just want to make sure. So let me run this. So we'll run this at the same time, and so you can kind of follow along. So if you ask, what is the Ames recipe right now? It's just going to say it's a recipe. So far, all we have are 1 outcome variable and 3 predictor variables. Okay. I don't know. I didn't print out here. I don't have the messages turned on. Okay. We can also do add some steps here. Okay. And so we can say these are how I want it to start preparing or doing some pre-processing here, okay? So let me just kind of, if I just take my basic recipe as it is, and if I call prep, let me just call I'm going to save this as prepped recipe. So right now, if I just prep it on the Ames training, and then if I bake the prepped recipe on Ames train, okay, all it does right now, So if I just take the recipe in its current form, which really is nothing, it just basically selects the variables. Okay, it just says, okay, the data that we need if we're going to run this recipe is we're going to just select this column: gross living area, year built, bedrooms above ground. Okay. Let me just kind of let me save these. Steps, so I can just kind of copy paste this really quick. All right, so so here I'm gonna just say we'll do step scale. We'll scale gross living area. Okay, so I'm gonna fix my recipe. I'm gonna just take my recipe and I'm gonna just add one step right now. Okay. So if I do this, my Ames recipe says this, and we're going to do one operation, a scaling operation of gross living area. Okay, and so if I run the same kind of thing here, where I'm going to prep the recipe and then bake the recipe, okay, you can see what it has done. It has scaled that variable gross living area. So the previous operation, oh, I cleared out the screen. But you can see if I look at Ames train, and if I just select gross living area, okay, you can see the actual values originally are what, 882, 864, and it transformed these into 1.76, 1.73. Okay, so when I bake my recipe, it applies whatever scaling transformation it is. Okay, and so we can kind of see, like, I can ask, what does my prepped recipe look like? Right, and it says, oh, okay, we've trained. This has been trained on GR living area. I can ask, now that my data has been baked, why am I struggling with this? Take my baked thing. Okay. And then I can just say, hey, let's look at this variable, gross living area. Okay, and then, I don't know, let me summarize. And we'll calculate mean of standard deviation. I don't know. Okay, so we have, so what it has done, scale, it just transforms everything, so the standard deviation is just 1. Okay, but it doesn't center it, so the mean is 2.99. Okay, so scaling divides everything. Okay, and then normalize will center and scale it. So here, let me fix my recipe here. I already have the scale, so we'll take the Ames recipe, and so now my Ames recipe has 2 steps in it: scaling for gross living area, center, and scaling for year built. Okay, and so I can again prep the recipe and bake the recipe. Okay, and so we can see year built has been transformed, and I can like, if I want to select, or I can just call summarize on this summary. Okay, and you can see for year built, the mean is now 0, right? And it's been scaled so that we're going to have a standard deviation. Of 1. So these are the steps that we've done. Okay. So step scale will divide all of the constants so that the standard deviation is 1 and it's not going to recenter the data. Okay, and we'll add another step for normalize. And so this is our recipe again, our Ames recipe. Scaling operations for that, centering and scaling for that. Okay, and then yeah, we can take our data and call prep, and that's going to be our prepped or trained recipe. So I can take my Ames recipe and call prep, and because so this will be trained, okay, and then you know, during kind of the prep function, you can call additional options such as log changes or verbose. Okay, so if I do log changes true, verbose equals true. Okay, I guess here what happens if I maybe the default is true, and I can say false. I don't know. Prepped recipe. What's the difference here? Let's do 12. Okay, here we're getting additional information. So the verbose output says same number of columns, retained training set now takes up this much space. Okay, and if you want to view the training data after pre-processing, you can do so with bake. So I can kind of take our pre-processing thing and I can call it. I guess I could call it on the training data, or I can just leave it as. I call this trained recipe, sorry. Not prepped recipe. All right, so we'll call this so pre-processed train. And so you can see, yeah, this is what the data looks like after all of those transformations have been applied. All right, and so here I can call glimpse. And so all of these things about like what's the mean and the standard deviation, we can see how after pre-processing, the mean and standard deviation is now, you know, over here it's 0, the mean is 0. Here the mean, it was not centered, it was just scaled. Both of these things have standard deviations of 1. Okay, we would then take our trained recipe and apply it to our test data. Okay, we would call bake on the test data. And if I ask about the test data, after it's been pre-processed, we can see the transformations have been applied as well, okay, for our test data set. And again, because the test data set is a little bit different, if I ask what is the standard deviation on our test data set for gross living area, that standard deviation is not exactly equal to 1. Okay, standard deviation for the year built variable is not exactly equal to 1, and the mean is pretty close to 0, but again, not exactly equal to 0. It's on the order of 10 to the minus 5, which is pretty close to 0, but on the actual data set, it is on the order of 10 to the minus 15, which in terms of floating point math, that is effectively equal to 0, and this is something that's just small. So this is the process of kind of doing our learning our parameters from our training data and applying them to either the training data or the test data. Okay, so let's continue on. So we have additional steps that we can do. Okay, so here we're going to just this doesn't do any kind of transformations. We're starting with a new recipe. We have a fourth variable. Okay, I'm sorry. Yeah, we have 4 variables. neighborhood, which is going to be categorical or nominal. Okay. Gross living area, the year built, and then the building type. Okay. So we'll do this. Okay. Step log will apply a log transformation. So it'll take the size of the home and then do a log transformation. So it's not going to center and scale, it'll do that. And then step dummy will make, you can specify things like, I want you to do this creation of dummy variables for all nominal predictors. Okay, so basically neighborhood and building type. So let me, okay. So when we take a look at simple image, I'm sorry, I'm gonna have to republish my notes because it is not outputting, it's not outputting the messages here. I apologize, okay? So here we have 4 predictor variables, 1 outcome variable, okay? And then I'm going to train this recipe. Okay. And so we get this this output. Okay. So as far as step log, we end up with the same number of columns because all we've done is we've just log transformed. But then when we make dummy variables for neighborhood, it says we have 32 new columns. Okay. And then, but I guess it ends up removing, and then, so we have 32 new columns when we do the dummy step. So we get neighborhood for all of these different neighborhoods, and then it deletes the original kind of neighborhood column. So, so this is what we have, and then, so let me just show you big new data. This will just go ahead and do it on the trained data. Let me call view here. Versus if I just have the original recipe where I'm selecting only these neighborhood. Okay, so if I just do So here in the original data set, our first observation is in the North Ames neighborhood, first 2, and then we have Briardale, okay? And then after I bake my recipe, you can see now we have a whole bunch of columns. We have a column for basically every single neighborhood. College Creek, Old Town, Edward, Somerset, and so, what was it? North Ames, okay? So one of these neighborhoods, one of these columns will be North Ames, and we should have, okay, I guess North Ames is going to be our baseline. So when you make dummy variables, like if your original data, if you have X is if you're gonna, let's say you have A, B, C, and C, okay? When you do a step dummy, you're gonna get columns. You're gonna get X underscore B, and then you'll have X underscore C, right? And here you'll have 0, and then this will be a 1, and then these will be, that's what you'll have that. That's step dummy. If you, there's also something very closely related where if you have It's called one hot. And it's the same idea here. If you have A, B, B, and C, C, okay? Basically, you'll get a column for XA, X underscore B, X underscore C, and then you'll have 1, 1, 1, 1, and 1, 1 here. Okay, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1. Okay. The default is this, okay? Because this now has redundant information. Like if you know, as far as the variables that start off with X, you know that if these are zeros, then it has, like, the one that's left off, X underscore A is a 1, right? So there is, like if you feed this into your linear regression model, now you have, the word, okay? But you have like columns that are dependent upon each other, right? And so like the inverse of your matrix will have a singularity because you have like linearly dependent columns, okay? And so so there's redundant information in this one. So one hot encoding, so the default is to just basically throw away this column here. So anyway, I guess North Ames is going to be our baseline here that gets thrown away, but then we can look at Briardale and North Park Villa, and we can see, yeah, we got the columns for Briardale, and then North Park Villa, and so on and so forth. Okay, so this is how it has done the dummy encodings there. And so we can kind of see some of those changes. Similarly, as far as the building type, when you look at the data, you have 1 fam, 2 family, connect, I don't know, something, duplex, townhouse, townhouse E, I don't know what those things are, and so here we end up getting 4 additional columns. Okay, and again, it has gotten rid of this one column, the column for 1 fam. Okay, if you do again 1 hot equals true, then you can get that redundant column there. All right. So yeah, on step dummy, by default, if there are C categories, step dummy will create C-1 columns, and so on and so forth. If you do want that column, you would call 1 hot equals true. Oops. Okay, so we'll pair the recipe together with a workflow, or with a model to establish a workflow, and then we can have different recipes and different workflows and things like that. So so for this, we'll create a basic model. This will be our linear regression model. So we'll just do linear regression. We'll set the engine to LM. Okay, and then we're no longer run it this way. Okay, we're not going to do the recipe, prep it, take the trained recipe and bake it. Okay, instead we're going to just run the workflow. Okay, and so if we did kind of the prep and bake steps, we would prep and bake, create our fitted model, and then we would then bake the test data, and then we would call predictions on the baked test data. Okay, and so the workflow, we just combine a recipe and a model. And so as far as a workflow goes, you establish it. You start off with a blank workflow, and then you say, hey, we're going to take this model, this recipe and this model, okay? And so that's going to be kind of just our basic workflow here. And then so once you have this basic workflow, then the process of kind of training and making predictions and whatnot is greatly simplified, okay? So you don't have to do this prep and bake, okay? You can inspect the workflow itself and just kind of see like, what is it? And so in this case, the workflow, our preprocessor is a recipe, our model is a linear regression model. As far as the recipe goes, it says there's 2 steps. We're going to do a log transformation for one of the variables. It's going to be the gross living area, and then we have a dummy. We make dummy variables out of the nominal predictors. And so as far as doing our workflow, we just fit it. We fit it to the data. So we're going to get our fitted workflow. Fitted LM workflow, we just take our existing workflow and call fit to the training data, and we can inspect what this fitted workflow looks like. Okay, and so as far as the fitted workflow goes, it says, okay, we trained it, and we've done this pre-processing, and it returns basically all of the coefficients. Okay, so these are the different coefficients for the different, I guess, neighborhoods, now that we've made them into dummy variables. It says there's even more. And then we can call make predictions. All right, so we take our fitted workflow and we'll call predict on the test data. So again, this skips the workflow automatically understands the process of prepping and baking. Okay, so once it's fitted and you say, hey, I want to make predictions on the test set, it's going to do that process of baking the test data. Okay, it's going to apply all of the transformations automatically to the test data. So you don't have to remember to do that step. Okay, normally you would, like if you were doing this manually, you would say, okay, now I have to scale or apply these dummy transformations or anything like that. And instead it just spits out the predictions. Okay. If you do want to get like that prepped recipe, okay? If you want to get like the in the workflow, if you want to kind of like get the intermediate step and say like, oh, I do want to see what my baked data looks like and all of that stuff, you can, okay? So all of these things, when you have workflows, it sets everything up very quickly, but if you want, you have options to kind of like inspect any of the steps along the way. So if you want to say, hey, I do want to look at what my prepped or baked data looks like, you can extract the recipe and then you can then bake it. You can call bake on it. New data equals null. That's what I want to write. Do I need to say retain equals true? I don't know. No, it doesn't like that. Oh, I broke something. Okay, but you are able to kind of extract out the recipe along the way. If you want to extract the fitted model, okay, you can also do that as well. So you can, from the workflow that we have fit, so remember we fitted the workflow, and you want to extract out the kind of all of that information. You can extract that model and then tidy it up, okay? So all of these things. So the workflow is really just kind of like, what is it the thing that you're after? Probably the thing you're after is just the predictions, okay? Because that's ultimately our goal for so many of these things is we just want to look at what kind of predictions we get and compare predictions to the actual values and measure its performance. But if along the way you want to kind of see the intermediate steps, even though you are using a workflow to kind of speed everything up, you can. You can extract the fitted model, you can extract the fitted recipe, and all of that along the way. So there are a whole bunch of different kinds of recipe steps that are available for you. So if I go to Tidy Models, you can look at the package recipes, and under reference there will be a list of all of the different functions that are available. Okay, the Tidy Models packages are some of the best documented packages out there, in my opinion. So anytime you want to learn something, I would say go to the website and learn about this. Okay, so there's a whole lot of information. So if you just go to Get Started, you have examples about some of the things, and so you can kind of see, we're doing something very similar. They take the original data, do a training test split. Here, this recipe is just basically select all predictors, but here we have other different kinds of steps, and so this is an example of the different kinds of steps, but you can do impute and things like that. And so as far as the documentation goes, you can see all of the different kinds of functions that exist. You have imputation functions, individual transformations, discretizing, dummy variables encoding, date and time functions, and things like that. So this is where you do any kind of feature engineering and stuff. So if you have date information, perhaps you want to extract out the month, okay? And you want to say like, I want to pull out the month and things like that. So anytime you want to like add new columns and stuff, I would say write a recipe that will do these operations, okay? Rather than manually processing the data, okay? So the classical method is you have your raw data and you say, okay, I'm going to start creating these new columns. I'm going to, and you might have a more efficient way to do it. You might write a script and you'll say, here's a script that's going to create new columns and do this and do that. But if you're able to make your script a recipe, okay, then you can throw it into a workflow and it will kind of automatically process everything along the way, okay? So here I've just highlighted a few of the different kinds of recipe steps that are out there. Oh, well, I guess there's additional recipe steps. I'm sorry, I'm jumping ahead of myself. I've highlighted them at the very end, but let's, sorry, getting ahead of myself here, okay? So some of the recipe steps, we have, one of them is called step unknown, okay? So this I just took straight from the textbook. It says, one of the most common feature engineering tasks is transforming basically categorical variables so that they can be encoded or represented numerically. And sometimes you end up with a kind of categorical variable where a certain, like some of the observations or some of the categories just rarely show up. And so it's really difficult to estimate a proper coefficient, okay? So for example, you might want to learn about like what type of, like the building type, okay? And you can say, okay, we have single family homes, we have, townhouses, we have condominiums, we have, I don't know, manufactured homes and things like that, right? perhaps in your data set, there are maybe like 2 or 3 observations that are some weird type, right? Maybe underground bunker, okay? And there's, you only have like a couple observations. And it would be, if you only have a couple observations, basically any kind of coefficient estimate that you try to get for that thing is going to be inaccurate, okay? And so rather than trying to, and you might have some of these like multiple categories, right? So you might have like a bunker, and you might have, I don't know, treehouse or something, right? And rather than trying to estimate all of these things, you can just do like an other, okay? You can also have step unknown. This can be used to change missing values to some kind of dedicated level. And step novel is, what do you do if in your test data set a brand new level appears that you've never seen before, okay? How do you handle something like that, okay? And so these are some of the options: step unknown, step novel, and then step other can be used to look at, you know, basically how common a particular category is, and if it's below some kind of threshold, we just kind of group them together, okay? So so here we can say, hey, let's look at our neighborhoods, and you know, some of our neighborhoods you know, barely show up in our data, and so if they're kind of the bottom 1%, we'll just kind of lump them together into a new level called other. So here I'm adding this step called step other, and we do this. You do the step other before you do step underscore dummy, okay? Because the dummy is going to turn everything into columns of zeros and ones, and so you want to do the other thing, which is going to just replace some of the categories. So if you have, like, you know, different colors, red, orange, yellow, green, blue, okay? And then you have, like, I don't know, gold. And gold very rarely appears, or something, you know, gold and silver rarely appear. You might just turn both of those. Everything that's gold just gets turned into other. Everything that's silver just gets turned into other, okay? And then at the end, then you do the dummy transformations. So, so this is, we're going to update our recipe as such, and we can kind of take a look at this here, right? So our simple Ames recipe, I can prep on our training data, and then I can bake it. And you can see, if I view this, one of my columns for neighborhood is going to be other, okay? And it looks like this, these observations, whatever they were, got turned into other. I wonder if perhaps maybe in the textbook it had a, okay, so this is basically what step other does, is it takes a look at kind of all of these different neighborhoods, and it says, you know what, some of these neighborhoods like Landmark, Green Hills, and things like that, those are going to just get lumped into other, okay? So if you look at the categorical variable, some of these things show up very, very infrequently, and so we're going to put those into category other, okay? And so that's what step other does. Okay. We can also include interaction terms, okay? And so interaction terms are like when different variables seem to have some kind of interaction, and so when you look at some of these different variables, okay, in general, when you look at gross living area and sale price, okay, for one family homes, we see that as the area of the home increases, the sale price also increases, okay? And that's true for townhouses, also duplexes as well. But for whatever, kind of less so for this, but this building type, whatever it is, two-family con, I'm not quite sure what that means. Bigger homes don't translate into larger sale price, okay? So here we want to kind of say like, yeah, you know what? Gross living area, this gives us information about sale price when it's one family homes, but not so much when it's this, okay? And so we might want to include an interaction term there, okay? And so, if you were to do something in base R, you would have to use kind of the star in your formula to indicate an interaction, or you'd use a colon, okay, to indicate an interaction between these things. And as far as recipes go, okay, you would use something like step interact, okay? So we already have these dummy variables. How do we combine some of these for interactions, okay? We'll add the interaction after the dummy step, and we'll say, hey, look at the interaction between gross living area and any of the variables that start with building type. Okay, so now my recipe has gotten bigger. Okay, so we're still doing a log transformation. We're gonna take our neighborhood variable, make other variables out of them, make dummy variables out of all of those things, and then now we want to look at interactions between gross living area and anything with a building type. Okay, so all right, and so I just want to kind of show you what this looks like. Okay, so we have gross living area, year built, sale price. We have all of the dummy variables for the different neighborhoods. Okay, as I scroll to the right, we also have dummy variables for all of the building types. Okay, and then now I have interaction terms. Okay, I have interactions for gross living area, building type two-family, gross living area, building type duplex, gross living area, and building townhouse and things like that. Okay, so for example, and we can see like this one we have a 3.038223, and basically it's just doing a multiplication operation. Okay, so if I look at this, it's the gross living area, and we're multiplying it by the variable building type townhouse. Okay, and so these are ones over here, and now we have an interaction there. Okay, so these are our interaction terms between basically these variables for the building type variables, those dummy variables, and the gross living area. Okay, so the order here is that the interactions come after the dummy variables. Okay, sometimes you want to do some kind of transformation to a numeric variable. Okay, so for example, you might want to do a log transformation. That's one of them. You can do polynomial transformations, and then sometimes you want to do a transformation that is more complicated than just a log transformation or a polynomial transformation. And one of the kind of flexible tools that are available to us is the natural spline. Okay, and so the natural spline basically just tries to take a look at the different values that you have and just tries to fit some kind of smoothed out curve here. So here's a diagram of some of the different possible splines. This variable is latitude. Okay, so one of the variables we have geographic information. So we have longitude and latitude. Okay, and so longitude would be where it is east to west, and latitude would be where it is north to south, right? And yeah, depending on the city, you might say like, oh, the east side of the city, has a bit more industrial stuff, and so perhaps the housing prices are not as nice. The west side of the city is, that's where like the fancy homes are, right? I mean, that's kind of how it is in Los Angeles, right? So you have like West LA, which is generally higher property values versus East LA or things like that. I mean, just strict property values, but it's not a very simple, like, it's not a linear thing where, on the east it's very low and on the west it's very high. There's going to be pockets where it's high value and pockets where it's lower value and things like that. And similarly, north south, there might be some kind of trend. And so, it might be worthwhile including these variables, but it might also not be something where you just want to model it with just a straight linear thing. And so splines give us some flexibility in terms of having a nonlinear relationship, but you can have all kinds of things. And so with splines, you have something called like the degrees of freedom, or your complexity. And basically, as you increase these things, you get basically a more and more flexible kind of curved fit, okay? So here, this is a spline with 2 terms, and it's kind of not showing much flexibility. With 5 spline terms, we have this. With 20 spline terms, we have this. And 100 spline terms, now it's like very kind of wiggly. And it's just kind of this idea of like, if I had to try to fit a smooth line to kind of fit everything, so, as far as latitude goes, going from south to north, it does seem like the northern side of the city, at least once you get past this point, the farther you go north, your property values seem to increase. But then, there's something kind of going on over here where, I don't know. I don't quite know what's going on, but there's like a dip down here, right? So you might want to include something that allows for this nonlinear relationship. And you have different things. The step log is one way to kind of do this, but another one is to use step ns, which will allow for you to fit a natural spline. Okay. And so we can throw in, I want to turn my latitude variables and my longitude variable into a natural spline. And then how many degrees of freedom do we have? And you can throw in some arbitrary number, okay? Higher number, more flexible, that's going to be kind of your high variance. And then the smaller number will be kind of your low variance but higher bias type of thing. So this is what our recipe looks like. And you can throw Ames recipe into this kind of universal function tidy, which will just present all of the information about the recipe in table form in case you wanted to, I don't know, do some operations with it. But here it just says these are all of the things. Right now it hasn't been trained. All we've done is we've just kind of declared the steps in our recipe. So it hasn't been trained or anything. So this is what we have. And then what we can do is we could throw that recipe into our workflow, and then we'll fit our workflow to our training data. Okay, so our workflow is consists of a model and a recipe and a model. And then we're going to just take the workflow and fit it to our thing. And this workflow will automatically prep the recipe on the training data, bake the recipe on the training data, and fit the model to the baked data. Okay, and that's how it's going to go. And then we could then run the same kind of recipe or the same kind of workflow on the test data and things like that. Okay. These are a bunch of different recipe steps that I wanted to highlight as far as feature engineering goes. And again, the true kind of reference is available here, and you can kind of read through all of them. And honestly, ChatGPT and AI is a useful thing when you want to say, hey, I want to use tidy models, and I want to apply this pre-processing step, okay, but I'm not quite sure which function to use, okay? And it will say like, oh, sure, the function you want to do is, I don't know, is this one or something, okay? All right, I want to do this. So rather than just leaving it open-ended, just say, hey, what is the name of the function that I need to use in order to do this? Okay, so normalize, this is a scaling thing. This is recommended anytime you have something sensitive to distances. So if you're going to do anything like lasso, where the size of the coefficients matter, k-nearest neighbors, k-means clustering, these are all kind of distance-based operations, and we haven't really talked about them, but sometimes you use distances as a way to measure similarity between observations. And so in those types of models, you want to normalize, okay, your variables so that, you know, one variable might have been recorded in terms of like centimeters, okay? And then another variable, you know, for example, let's say you're gathering information about people, and you say maybe you have their height measured in centimeters and their weight measured in kilograms or something like that, okay? Then, you know, the height is generally going to be a much larger number than, say, the weight, right? So you might have somebody who's 70 kilograms, okay, but they might be 190 centimeters tall, right? And so you're going to have a higher standard deviation for the height versus the weight and things like that. And so anyway, normalize will kind of put everything on, you know, turn everything into z-scores, okay? And so that's going to be step normalize. Normalize really only makes sense to do it on numeric predictors, and you have these kind of, you can specify the actual columns that you want, or if you just want to kind of just say, hey, do it to all of the numeric predictors, you can just use this as a selector function, and it will pick all of the numeric predictors, okay? Other is going to lump infrequent factors into the other category, and so we saw an example of this, you know, as far as neighborhoods. Rather than having all of the neighborhoods, you might just kind of take the most infrequent ones and put that into other, right? So like hair colors, okay? You can have black hair, brown hair, blonde hair, red hair, and then you might have, like, you know, for people who dye their hair, you know, purple and pink and blue and whatever, you might just have an other category or something like that, okay? Sometimes you end up with columns with zero variance, okay? So that basically means this particular column, all of the values are exactly the same. That's what it means to have zero variance, right? Every single value is the same. So maybe like it's a numeric thing. It's like, how many fingers do you have? And in your data set, every single person had 10 fingers, okay? This is not a useful predictor, okay? And so zero variance basically means you have no information. This variable isn't providing you any information, and you can just, step ZV is going to get rid of them, okay? And so that basically gets rid of useless columns, right? Or if it's a categorical variable, you know, what school do you attend? And in your data set, everyone says, I go to UCLA, okay? You know, not a useful predictor. Yes, question.
Should we use that function like at the start before we do any other methods? Or is there a specific order?
Yeah, there is a specific order. Let me think where zero variance would go in. Yeah, I mean, at the very beginning, that's probably when to use it. I'm trying to think if there's like an after transformation, if you end up getting a zero variance column, how often does something like that happen? I'm trying to think. Yeah, I don't know. Can't think of an example off the top of my head. If like you after you transform a variable, if you'll end up getting a zero variance thing, I'm not sure. But yeah, generally this one is pretty safe to do at the beginning. Okay. Impute missing values with either impute median or impute mode or impute mean, I guess. And so that's a very rudimentary way of filling in a missing value, and it's not necessarily always the best. Okay, but if you have something where having a missing value will prevent you from using that observation, okay, maybe it's reasonable to just kind of plug in a value. Okay, so if you have numeric values, probably you'll impute the median or something like that. Impute mode would be used for like a categorical variable, and you'll just kind of plug in the most common categorical response, right? So like, what country? All right, what country are you from? And you might have people from different countries and stuff, but someone you have a missing value, you might say, okay, well, in my data set, most common response was United States. So we're just gonna assume this person's from the United States or something like that. Okay, that's impute. There are other things as far as imputation goes. So you can impute via k-nearest neighbors, and so it'll look at like the other variables and say like, okay, based on the other variables, I'm gonna think this person is from the United States, and so we'll plug in the United States. Okay, based on the other variables, I'm gonna think this person's from Mexico, and we'll plug in Mexico or something like that. Okay, this one it does take a little bit of impute with. You'll say use these variables as far as which variables you want to use to try to guess what the missing value is. Okay, so that's so this is kind of a neat thing. Other things you can also impute data using the mean, median, most common value. Let's see. Step. Okay, unknown. Unknown is just like if it's missing, you just replace it with a value of unknown or something like that. Okay, and it feels like, oh, how's that different from missing? It's just gonna basically plug in something there. Okay, so that you'll have a dummy variable for the column unknown, and you'll get like a 0 or 1 there. Okay, versus just like it's missing. So those are some other operations that are available. So these are all things that you can do manually yourself, but having the recipe will just kind of streamline everything. And then the equivalent, and I don't have any kind of slides or notes on it, but if you're using Python and scikit-learn, the equivalent would be establishing pipelines. And there's a whole bunch of functions there. Yeah, okay. Log transformations. You can just kind of do log transformations and again, you probably won't do all numeric predictors, but just some of them, the ones where it makes sense to do a log transformation. And then there's also offset 1. Okay, so obviously you can't do logs of negative numbers, but also a log of 0 gives you negative infinity, and that often blows things up. So an offset of 1 will just basically add 1 to like all of the values so that you don't get a 0, and then you can do the log that way. Okay. So at least the offset 1 is frequently recommended, and that will also make ensure all of your log values are positive. Okay, or at least non-negative. Other things. Okay, interact. Okay, so we saw things as far as interaction terms go, and you can, this will multiply all of those things. Okay, these are nonlinear transformations, and so we saw natural spline, and you can specify the degrees of freedom, but then you can also do step poly, and this will do, polynomial things. There's also even more here, and I don't know, actually don't even know what some of these things are, or a lot of these things. Okay. So I have no idea what is. I've heard of this. Box-Cox transformation for non-negative data. I remember. What does that one do? It's something, right? Do you guys cover this? Box-Cox transformations? I forget. Okay. Okay. Inverse logit, the logit transformations. Yeah. So these are things like if you want to do logistic regression, you can do a logit transform and inverse logit. A lot of these kind of nonlinear transformations you can do. There's also multivariate ones. I don't have any examples of this, but or actually I do. I think I do PCA, but or I at least mention it. And that's probably the most common one. But there's a whole bunch of these things that I'm not so familiar with, but they are available as far as options for transforming things. Yeah, so step PCA, okay, so I have not directly covered principal components analysis, okay, but PCA tries to find, will transform a lot of kind of like highly correlated variables into a handful of uncorrelated variables. Okay, so it's often used for dimension reduction. So in terms of like the housing data set, you're going to have a lot of these variables that are highly correlated, like the size of the house is going to be correlated with the number of bathrooms and the number of bedrooms, right? Bigger houses, more bedrooms and bathrooms. Smaller house, fewer bedrooms and bathrooms. And so, your traditional approach would just be like, okay, we'll just keep the size of the house and we'll throw out bathrooms and bedrooms, okay? But PCA will do some kind of linear combination, and we'll say like, okay, we'll take the size of the house and add 0.5 times the number of bathrooms and minus 0.2 the number of bedrooms or something, and this is going to give us some other variable that manages to capture more variance or something like that, okay? And there's a mechanism behind it. What it tries to do is it tries to maximize the amount of variance captured in your principal components. And so you would do something like step PCA, all right? And then so almost always when you do PCA, you're going to normalize your variables first, okay? Because PCA is dependent upon like the magnitude of the values. And so you'll want to normalize first, otherwise your PCA analysis will be thrown off. And then during your PCA, you'll say, these are the number of components I want to keep. So you might have like 50 variables, and it's going to do some kind of PCA analysis, and you can just keep the first 5 or something. And so this is going to be dimension reduction, removes multicollinearity, okay? A big drawback of PCA, though, is your principal components will be gibberish meaning, okay? Like, if you have the variable number of bedrooms, like, you know what that means, okay? But now if you have this mystery PCA variable and it says, oh, this house has a score of 2.7, I don't know what that means, okay? And then PCA can't do deal with missing values, so you have to impute values and things like that, okay? And then it is important that you do step normalize, because that's going to throw off your PCA results if you don't, okay? Step core is like another way of handling multicollinearity. And so step core is going to just remove predictors that are highly correlated. I forget exactly so this is the high correlation filter, and it will remove variables that have large absolute correlation. So let me think. I think it just keeps one variable and it throws out the ones that are highly correlated, but let me see. So this step is going to remove columns from the data set, and this could cause issues if the missing columns are referenced. So saving recipes and filtering columns, okay. So this step attempts to remove variables to keep the largest absolute correlation between the variables less than threshold. When a column has a single unique value, that's going to be excluded and things like that. Okay, so yeah, basically if you have these two columns in there, I don't know, it could be like, what's an example? You know, like you have information about the neighborhood, and it's going to be like median house price of the neighborhood and like median income of the neighborhood. Okay, those are probably going to be highly correlated. Maybe it only makes sense to include one of those variables, and so this is the high correlation filter. Okay, and so, you know, as you're doing your things, you know, you might wonder like, well, why should I even throw away some of the variables? Again, having too many variables, especially ones that are highly correlated, you know, will add noise and stuff. Okay. Step RM just removes variables entirely. So, especially if you have columns like the ID column or the name column or a text column that's not going to be useful, just throw those out. Step RM gets rid of those. And then mutate, step mutate will allow you to just directly create new variables within your recipe itself. Okay, so this is just an example, but you can calculate some kind of ratio between two variables or something. So again, what we traditionally did manually, we can now kind of automate inside a recipe and include in a workflow, so to kind of keep our data analysis workflow very smooth, our pipeline very kind of smooth and efficient. Okay. Oh, there's discretize. So sometimes you have a numeric variable and you want to like group them up. Okay. So this will basically create bins. So you can take age and you can discretize it, and it will say like, this is, you know, age, you know, one age group, you know, older age group or something. You know, we have something similar, like the idea of that in like generations, right? You have boomers and Gen X and millennials and Gen Z and Gen Alpha or whatever, right? That's basically, you're discretizing a numeric variable, right? And that might be more informative than saying like, oh, this person is 22 versus this person is 26, having and versus this person is 40. Knowing the exact number might not be as useful as just saying like, oh, this person's from this generation or this person's from this generation or something like that. So step discretize will do that. And then step dummy, we've already seen step dummy, but basically it turns your categorical variables into numeric ones. Okay, that's all I got for now. So we'll end a little bit early today as far as recipes go. So that's that, and then we'll start applying this. So I just do want to encourage you to try to establish your groups, and probably sometime next week, if you're not in a group, I'm just going to assign you to a random group, okay? But we'll see you guys next week.